Hello everyone, welcome to Infotainment Lounge. My name is Khurram Akhlaq and today's video is about electronegativity and intermolecular forces of attraction. And this video is for AS level chemistry. So electronegativity, it is the ability of an atom to attract a shared pair of electrons towards itself. And yes, when we are talking about a shared pair of electrons, we are talking about a covalent bond. Suppose we have two atoms and they have a covalent bond between them. This covalent bond is the shared pair of electrons. This pair of electrons is being shared by both the atoms. Now there is a force of attraction from this nucleus which is pulling this electron pair towards itself. That force of attraction is called the electronegativity of this atom. And similarly, the nucleus of this very atom will also be pulling the shared pair of electrons towards itself, and that force of attraction is the electronegativity of this atom. Now electronegativities could be same or different when two atoms are bonded to each other. Now commonly when the bonded atoms are of same type, like in Cl2, they are both chlorine atoms, so they will have obviously equal electronegativities. But in case of different atoms, like if you talk about the bond between hydrogen and chlorine, this hydrogen chloride, this shared pair of electrons would be attracted with different forces towards each side. Chlorine has a different electronegativity, hydrogen has a different electronegativity. So this electronegativity is the base of the origin of intermolecular forces. Not all of them, but most of them. But how can we know that which element has a greater electronegativity and which element has a smaller electronegativity? You can pretty easily observe that by looking at the periodic table if you know the exact trends of electronegativities. You need to remember that down the group, electronegativity decreases, and this is because of increasing distance of the valence electrons from the nucleus. Because of that, the effective nuclear charge decreases, so the force of attraction from the nucleus on that shared pair of electron is also decreasing. And when you move across a period, in general the ionization energy increases. That means, and that is because the outermost shell is the same. That means there is no significant change in the radius of atom, but there is a consistent increase in the proton number. That means nuclear charge. So nuclear attraction is increasing, so obviously electronegativity would be increasing across a period when we move from left to right. So keeping this in mind, now let us take a look at the intermolecular forces. There are three main intermolecular forces in your syllabus, in the syllabus of AS level chemistry. One is permanent dipole force, other one hydrogen bonding, and the last one is temporary dipole induced dipole force. Today I will try to explain all three forces. Okay, so let's start with the permanent dipole force. Now permanent dipole force, it is actually directly related to the bond polarity, which is directly related to the electronegativity. In fact, the difference in electronegativities between the bonded atoms. I'll try to explain it with an example. Let's take an example of hydrogen chloride. Now this is what a hydrogen chloride molecule looks like. But we already know that there is a nucleus in the center of chlorine atom with protons in it, which is pulling this electron pair towards itself, and there is a nucleus in the center of hydrogen atom with a proton in it, and that is pulling these electrons towards itself. Now we know by the trend hydrogen is on the left side of the periodic table, whereas chlorine is on the right side of the periodic table. So chlorine has a higher electronegativity than that of hydrogen. Now chlorine with a higher electronegativity will attract this shared pair of electrons towards itself with a stronger power. So this electron pair would move a little closer towards the chlorine atom, and it would move a little far away from the hydrogen atom. Keep one thing in mind, that there is a limit to what extent these atoms could come closer to each other, because in the center of each atom there is a nucleus containing protons, and those nuclei are repelling each other. So there is a certain limit. The nuclei cannot come closer to each other than more than that limit. So suppose here this is the nucleus of hydrogen, this is the nucleus of chlorine. This shared pair of electrons would finally arrange itself a little closer to the chlorine atom, whereas it would be a little further from the hydrogen atom, from the nucleus of the hydrogen atom. Okay, now keep another thing in mind, that in this case electrons are not being transferred from one atom to each other. In fact, they are just getting closer to one atom and just getting a little far away from another atom. This is not complete transfer of electrons. This is still sharing of electrons. But now due to this movement of electron pair, there would be partial charges. If there was a complete transfer of the electrons, then there would have been full charges and the compound would have been ionic. But in this case, compound is covalent. Electrons are not being transferred, they are still shared, but the electron pair is closer to one atom and farther away from the other atom. That is why they will have partial charges, and partial charges are represented with the sign sigma. Now chlorine, because this electron pair is closer to the chlorine atom in this case, so chlorine will have a partial negative charge, and the electron pair is farther away from the hydrogen atom, so hydrogen will have a partial positive charge. Now if you consider this molecule has more of a negative charge on this side and more of a positive charge on this side. Although they are partial charges, but still they are charges. That would make this part of the molecule the negative pole of the molecule, and this part of the molecule would be the positive pole. Okay, so that means this molecule has two poles, a negative pole and a positive pole, and these poles are permanent in this molecule. Why is that? Because as long as these two atoms are bonded to each other, they will always have different electronegativities. So this electron pair will never come closer to hydrogen atom. It will never move away from the chlorine atom. Its position would be like this, closer to chlorine, farther away from hydrogen. So this molecule, which has two poles, and it has two poles permanently, it's called a permanent dipole. This is why this molecule is called a permanent dipole. Now let us consider another molecule of hydrogen chloride right in front of this molecule. That molecule will also have a pretty similar arrangement of electrons. It would be like this. Now again, this shared pair of electrons is closer to the chlorine atom, so chlorine will have a partial negative charge. This shared pair of electrons is farther away from hydrogen atom, so hydrogen will have a partial positive charge. And again, if you split the molecule into two, this part of the molecule is the negative pole and this part of the molecule is the positive pole. And due to presence of these two permanent poles, positive and negative, this molecule is also a permanent dipole just like the other one. So now we have two permanent dipoles close to each other, and we know that opposite charges attract each other. So the force of attraction, there will be a force of attraction between the negative pole of this permanent dipole and the positive pole of this permanent dipole. This force of attraction is called permanent dipole force, or simply PD force. The next intermolecular force of attraction is called the hydrogen bond. Now keep in mind, although its name is hydrogen bond, but it's not a bond, it's an intermolecular force of attraction. And it is pretty similar to that of permanent dipole force. Just the difference is that the molecules are highly polar. They form dipoles, but their dipoles are stronger than other molecules like the ones which show permanent dipole force. Now which bonds are going to be highly polar? In order to understand that, we need to again reconsider the trends of electronegativities. Okay, now first thing is that which element or which set of elements would have the highest electronegativities in the periodic table. As we all know, noble gases do not form bonds, they are already stable, so we will not account group 18 elements. We would just look at the rightmost side excluding group 18 elements. And at the top we have fluorine. Before fluorine there is oxygen, before that there is nitrogen. These are the three elements with highest electronegativities. Whereas the element with the lowest electronegativity which forms covalent bonds is hydrogen. Hydrogen is to the far left side of the periodic table. I know you would say, why I am not saying that francium is the element with lowest electronegativity. Indeed it is, but the thing is, francium is a metal. Francium, rubidium, all those group 1 metals, they do not form covalent bonds, they are metals. Hydrogen is the one which forms covalent bond and it has the least electronegativity. So consider a bond between hydrogen and fluorine, or hydrogen and oxygen, or hydrogen and nitrogen. Any of these three combinations, HF bond, HO bond, or HN bond. These three sets of atoms, they have the largest difference in electronegativities. Due to the largest difference in electronegativities, again the same thing will happen, but to a greater extent. Let us take an example of hydrogen fluoride. Hydrogen fluoride, now fluorine has a far greater electronegativity than a hydrogen atom. In fact, fluorine's electronegativity is highest among all those elements which form covalent bonds. So yes, this electron pair would be closer to the fluorine atom and farther away from the hydrogen atom. So fluorine will have a partial negative charge, hydrogen will have a partial positive charge. But in this case, actually in any of these three cases, there is a huge difference in electronegativity. So the negative pole would be a pretty strong negative pole. And the positive pole will also be a strong positive pole. Another thing to addition, see, whenever anything is coming or passing by this side of the molecule, it has to face the positive pole hydrogen. Now hydrogen is an exceptional positive pole. Not only that, in combination with fluorine it would be a very strong positive pole, but also it only had one electron in its outermost shell, and that electron is now placed between both the atoms. So whatever is passing by this side of the molecule, it has to face the nucleus of hydrogen directly. So there will be an additional effect of the charge. Similarly, if anything is passing by this side of the molecule, it is not only facing a very strong negative pole due to high electronegativity of fluorine, but there are also lone pairs of electrons. They will have an additional effect of the negative charge. So because of that, the force will be stronger than the permanent dipole force. So if we have another molecule of hydrogen fluoride, it will have the same partial positive and partial negative charges. It will have strong positive pole and a strong negative pole, and the force of attraction between this strong positive pole, which has to be hydrogen, and the lone pair of this strong negative pole is called hydrogen bond. But keep this in mind that hydrogen bond is not a bond, it is an intermolecular force of attraction. So we do not represent it with full lines, we represent it with dotted line. It is not a bond, it is an intermolecular force of attraction. And you can define, in fact you can define hydrogen bonding as the force of attraction, the electrostatic force of attraction between the hydrogen atom of a highly polar molecule and the lone pair of a strong negative pole of a highly polar molecule. You always have to mention the lone pair. There is a specific role to lone pair in this molecule. For example, if you are representing this hydrogen bonding in a displayed form, in a displayed formula form between hydrogen fluoride molecules, you will not just do this. You have to do two more things. You have to mention that this has partial negative charge, hydrogen has a partial positive charge, same goes here, partial positive, partial negative, and there is a lone pair on the fluorine atom. That lone pair is attracting this positive pole of hydrogen fluoride molecule, whose positive pole is hydrogen. So there is no electron here. This lone pair is facing the nucleus of hydrogen directly. So the force of attraction is pretty strong as compared to permanent dipole force. Same goes with ammonia, NH3. Now we know that nitrogen has a far greater electronegativity as compared to hydrogen, so it will have a partial negative charge, whereas all the hydrogens will have partial positive charges. And nitrogen also has a lone pair of electrons. Now if another ammonia molecule is closer to this, the positive pole of that ammonia will arrange itself right in front of the negative pole of this ammonia. and the negative pole of this ammonia will arrange the positive pole will arrange in front of the positive pole of the other ammonia. Now there will be a force of attraction between this positive pole and this lone pair of electrons, and there will be a force of attraction between this positive pole and this lone pair of electrons, and this force again is the hydrogen bond. Let us take an example of water, H2O. Again, hydrogen is the positive pole, oxygen is the negative pole because oxygen's electronegativity is far greater than that of hydrogen. The positive pole of the other water molecule will arrange itself in front of the negative pole of this water molecule, and the negative pole of the other water molecule will arrange itself in front of the positive pole of this water molecule. Now there will be a force of attraction between this hydrogen atom and this lone pair of electrons, and there will be a force of attraction between this hydrogen atom and this lone pair of electrons, represented by a dotted line. These are again hydrogen bonds. So the strongest hydrogen bond in these three molecules would be in hydrogen fluoride, because fluorine is the most electronegative element of all. The second strongest hydrogen bond would be in water molecules. The third strongest hydrogen bond would be in ammonia molecules. But this takes us to a question. The question is that we know that hydrogen fluoride is a gas at room temperature. Ammonia is a gas at room temperature, whereas water is a liquid at room temperature. Technically, the melting and boiling points of these substances, they all depend on the strength of intermolecular forces. Now the strength of intermolecular force if we compare these three molecules, hydrogen fluoride has the strongest intermolecular force because its difference in electronegativities is the greatest. Before that, it is water, and the weakest among these three would be the hydrogen bonds formed in ammonia molecules. Now, according to that, their boiling points should be like this. The lowest one among these three should be ammonia's boiling point, then there should be water, and the highest should be hydrogen fluorides. But in reality, it's not the case. In reality, water has a higher boiling point than both of these. It is a liquid at room temperature. You may be asked in your examination about the reason behind this, and there is a very simple answer to that. See, the number of lone pairs in a water molecule is 2, and the number of hydrogen atoms in a water molecule is also 2. So it can form 2 strong negative poles and 2 strong positive poles. So overall, the number of hydrogen bonds per molecule is greater in water molecule as compared to ammonia and hydrogen fluoride. So irrespective of a stronger hydrogen bond of hydrogen fluoride, the boiling point of water is higher than hydrogen fluoride because it forms more hydrogen bonds per molecule than hydrogen fluoride. Okay, so last intermolecular force of attraction in your syllabus is temporary dipole induced dipole force, and this force is also called Vanderwaal force. You have heard this name in your previous classes as well, but you didn't know how this force exists. Now let us try to understand this. First thing first, see, this force of attraction will exist between non-polar molecules. Non-polar molecules, that means which are not forming permanent dipoles. Those bonds are called non-polar bonds and the molecules are called non-polar molecules. For example, we have Cl2, chlorine. There is a bond between two chlorine atoms. They have equal electronegativities, so the position of the shared pair of electrons will not change. It would not get closer to one atom and it would not get farther from the other atom. So the bond is considered to be non-polar. There will be no partial charges. Now let's take another example, like let's say nitrogen N2. There is a triple bond between two nitrogen atoms, but all the three shared pair of electrons, they are being pulled towards the atoms with equal forces. Their electronegativities are equal. Both atoms are of the same element. This is why those electrons would be arranged right in the middle of the atoms, so there will be no partial charges. And even the gases, like noble gases, which do not exist in the form of molecules, they exist in the form of their atoms. For example, neon, argon, helium, they are already not forming any bond, so there is no question about electronegativities or bond polarities because there is no bond. So even they are considered to be non-polar. And non-polar atoms or molecules, they have Vanderwaal force or temporary dipole induced dipole force. Now in order to understand this force of attraction, let us take the example of neon. It would be simpler to understand from that. Now neon, see, this is one atom of neon. It has two electrons in its first shell and it has 8 electrons in its second shell. It has a completely filled outermost shell. Now in diagram we see the electrons like this, but in reality these electrons are not in their fixed positions. These electrons are revolving around the nucleus in a spherical pathway, not even a circular pathway, it's a spherical pathway. That is why their positions are never fixed, they are moving at high speeds. Now considering that, suppose they are moving at a high speed around the nucleus in spherical pathways, and for just a moment, for just fraction of a second, the position of its electrons is like this. Coincidentally, for a moment, temporarily, for a fraction of a second, the position of the electrons, the arrangement of electrons is like this. Now just pause the movement of electrons for a moment. Now let us study this atom, how it behaves when the electrons are in this position. We can see that there is a higher concentration of electrons, there is a higher electron density on the right side of the atom, and there is a lower electron density on the left side of the atom. So overall, if we consider two halves of this atom, this half will have a weak partial negative charge due to presence of a greater electron density, and this part of the atom will have a partial positive charge. But suppose we have paused this movement of electrons. Whenever we press the play button again, they will start revolving again and there would be no dipoles again. So there is a dipole in this atom, but this dipole is temporary. This is the negative pole. This part of the atom is the positive pole. And these poles are formed due to the high speed movement of electrons around the nucleus. This is why this dipole is a temporary dipole. Now let us consider another neon atom which is closer to this neon atom. It will again have the same set of electrons, 2 electrons in the first shell and 8 electrons in the second shell, but due to this temporary dipole there is a negative electric field on this side of the atom, and we know that electrons too are negatively charged, and these electrons in the shells of this neon atom will be repelled due to this negative pole, and those electrons will move towards this side due to that repulsion. See, this was formed due to the movement of electrons. This is formed because of the repulsion of this negative pole. These electrons have shifted towards the right side due to the repulsion of the negative pole of this neon atom. Now again, if you divide this atom into two, this part becomes the negative pole and this side becomes the positive pole. This has a partial negative charge, this has a partial positive charge. This dipole was a temporary dipole. Now this dipole is an induced dipole because it was not there in the first place. It has been induced in this atom because of this dipole. So this becomes an induced dipole. Okay, again, none of these dipoles are permanent. None of these dipoles is permanent. This is a temporary dipole and this is an induced dipole. The temporary dipole will not last longer, and as it is not a dipole anymore, this won't be a dipole anymore too, because the induction due to the negative pole of this dipole would be eliminated. But as long as these atoms are in this position, there will be a force of attraction between the negative pole of the temporary dipole and the positive pole of the induced dipole, or vice versa. That force of attraction is called temporary dipole induced dipole force. Okay, so any molecule which is non-polar in nature, that means it is not making permanent dipoles, they will have this force of attraction, temporary dipole induced dipole force, because they still have electrons. It doesn't matter if they are polar or not, they still have electrons, and the electrons are revolving around the nucleus, and due to that movement there will be temporary dipoles formed, and when temporary dipoles would be formed, there would be induction of dipoles into the other atoms or molecules, and the attraction between the opposite poles of a temporary dipole and an induced dipole is Vanderwaal force, or temporary dipole induced dipole force. Now let us talk about the strength of temporary dipole induced dipole force. As we know that this force of attraction is originated because of the movement of electrons, so it would be directly proportional to the number of the electrons. The strength of temporary dipole induced dipole force is directly proportional to the total number of electrons in the molecule. For example, if we are comparing fluorine with chlorine, they are both non-polar. They do not form permanent dipoles because there is no difference in electronegativities, but chlorine has a higher boiling point than that of fluorine. Now why is that? Although they both have weak intermolecular force of attraction, which is temporary dipole induced dipole force, but chlorine has a higher boiling point. This is because chlorine molecule has a greater number of total electrons. Fluorine, the proton number of fluorine is 9, and there are 2 atoms of fluorine, so 9 times 2 is 18. there are total 18 electrons in this molecule. The proton number of chlorine is 17, and there are 2 chlorine atoms in total, so 2 times 17 is 34. The total number of electrons in a chlorine molecule is 34. So when chlorine atom forms a temporary dipole, it would be stronger than the temporary dipole of a fluorine molecule. Similarly, the induced dipole in the chlorine molecule would be stronger than the induced dipole in a fluorine molecule. This is why chlorine has a higher boiling point as compared to fluorine. Similarly, bromine, Br2, this will have an even higher boiling point. In fact, bromine is a liquid at room temperature. Although it has the weakest force of attraction, but still its temporary dipole induced dipole force gets stronger and it becomes a liquid. It is a liquid at room temperature. That is because it has a greater number of electrons. The proton number of bromine is 35, and there are 2 bromine atoms, so 2 times 35 is 70. It has 70 electrons, total 70 electrons in one bromine molecule. So when 70 electrons, when they form temporary dipoles, those temporary dipoles are pretty strong temporary dipoles, and the induced dipoles in bromine molecules would also be pretty strong. So the intermolecular force, temporary dipole induced dipole force of attraction, will be stronger in bromine, much stronger as compared to fluorine and chlorine. This is why it is a liquid at room temperature, whereas fluorine and chlorine are gases at room temperature. Now you may be asked in your examination to compare the boiling points of any 2 substances or even more. You may be asked to arrange elements or compounds in an increasing or decreasing order of boiling points. Keep these things in mind. Boiling points and melting points, they always depend on the intermolecular force of attraction. Stronger the force of attraction, higher will be the melting and boiling points. Weaker the force of attraction, there will be lower melting and boiling points. Now, among these 3 forces that you have studied today, permanent dipole force, hydrogen bonding, and temporary dipole induced dipole force, the strongest one is hydrogen bond, and the weakest one is temporary dipole induced dipole force. But the strength of temporary dipole induced dipole force has a pretty wide range. It starts from very weak, and the maximum value of temporary dipole induced dipole force is pretty high, like in iodine, in astatine, I2. It is a solid at room temperature. It can even dominate hydrogen bond, which is the strongest intermolecular force. Even water is a liquid at room temperature, but iodine is a solid at room temperature. That means this force of attraction, although it is temporary, but if the number of electrons is greater, then this force may dominate other forces of attraction. So keep this in mind, that the strengths of intermolecular forces and the internal chemistry of the intermolecular forces, this is a very important topic of AS level chemistry, and you will definitely see some relevant question in your examination. So you can practice as many questions as you can related to these intermolecular forces, and if you have any queries about these intermolecular forces or the electronegativities, you can ask me in the comment section. I will try to make another video in which I'll discuss the problems that you have quoted in your comments. I hope this video was helpful. I'll see you very soon again. Stay tuned. Until next time. Thank you. Allah Hafiz.